Good morning, everyone. My name is Neil Madden, and I'm going to be talking to you today about practical cryptography using Tink, which is Google's high-level crypto library. So a lot of introductory lessons on cryptography tend to cover the kind of theoretical aspects and what our secure construction is and modern best practices. But this talk is really focused on how you take that theoretical knowledge and translate it into working code and avoiding a lot of the pitfalls and implementation mistakes that can often undermine the security of your entire system. So to do that, we're going to look through old-style cryptography libraries, as I call them, which put a lot of emphasis on the developer knowing a lot about cryptography and how to use it securely. And we're going to talk then about how Tink and this new wave of modern crypto libraries steer you away from those kind of mistakes. So a little bit about me to begin with and why you might want to listen to me on this course. So I'm Neil Madden. I'm an independent security consultant, specialising in kind of application security, applied cryptography. I'm the author of a book called API Security in Action, which is all about how to secure your APIs, covers things like JSON Web Tokens and all that kind of stuff. And I've found a few big vulnerabilities in my time, and I'm also kind of a long-time contributor to the OAuth and JSON Web Token working groups at the IETF. So what is Tink? Tink is a cryptography library that's developed by Google. It comes in a range of different languages, so there's a version in Java, there's one in Go, C++, Objective-C, and Python. And they kind of aim to have the same functionality across those languages. There's a bit of gaps here and there where there's some things that work on one and not on the other, but the broad idea is to have the same functionality across all these languages. It was originally developed at Google by people who are expert cryptographers and crypto researchers. So a couple of people, Tai Nguyen, who's a Vietnamese cryptography researcher who's found several high-profile attacks against SSL, so the crime and beast attacks and things like that. And Daniel Bleichenbacher was also involved in Tink in the early days, who gives his name to various attacks against the RSA crypto system. They also, between them, co-developed another Google project called Project Witcherproof, and Witcherproof is apparently the smallest mountain in the world. And that is a kind of comprehensive regression test of almost every cryptographic vulnerability that's ever been found in the past. So it has all kinds of test cases for error cases in RSA and elliptic curve signatures and all kinds of things. So this is a kind of appeal to authority that these people kind of know what they're doing and they know how to attack crypto systems, and so they know how to kind of design secure cryptography. And Tink has been designed to be easy to use in a secure way and hard to use in an insecure way. And we'll go into some of the details of that in a moment. So the first example we're going to talk about is just encrypting a simple small file, like a data file for your application. Something quite small at this stage. We'll talk about bigger files later on. But the gold standard of encryption in modern days that you want to use is what's called authenticated encryption. It's sometimes called AEAD, which is authenticated encryption with associated data. And old encryption schemes generally only provided confidentiality, so they protected the privacy of the thing you were encrypting, but they didn't protect the data integrity, and so people could tamper with the data, and often in those cipher modes you can tamper with the data in a very predictable way. So you flip a bit in the ciphertext and it flips a bit in the plain text. So the kind of usual example is, you know, a bank transfer, you send a message saying pay Bob $200 or something like that, and Eve intercepts it in the middle and flips some bits because she can kind of guess what the format of the message is, and suddenly it says pay Eve $200, right? So what we want generally is both confidentiality and integrity, and in fact if we give up on integrity we often lose confidentiality as well, is the kind of modern results that we found out. And we generally want not just data integrity, but we want data origin authentication, which is also known as message authentication. We want some idea of where the message has come from, particularly in a lot of online applications and things where you're doing authentication and stuff. You want to have some assurance that this came from a trusted party. So AEAD provides all of that for us, in one thing, and it's kind of how you should be doing encryption in 2024. So if we look at an old style cryptography library, so this is the Java built-in crypto libraries, it's called the Java Cryptography Architecture, and it dates back like 20 odd years, 25 years maybe. And although this is specific to Java, it's also quite typical of crypto libraries of that time. So if this is how you want to encrypt a file, there's a whole load of details I need to know. So first of all, there's this very generic cipher class that I have to get an instance of. And that cipher class not only does authenticated encryption, it also does unauthenticated encryption. It does encryption schemes like ECB mode, which if you've ever seen the ECB Penguin thing, is this kind of terrible mode of encryption which doesn't really encrypt anything at all. It not only does these kind of shared secret symmetric encryption modes, but it also does public key encryption. So it covers this huge gamut of different security goals and security properties under this one very general abstraction. And because it's very general and has to cope with all those use cases, it means you as a developer need to know a huge amount about how it works. So for example, when you use one of these encryption modes, you have to supply what's called a unique IV, initialization vector. It's sometimes called a nonce in some modes, which just stands for number used once. So in this mode we're using is Galois counter mode, which is an authenticated mode, and you just have to know that as a developer that that's an authenticated mode. And so one of the things that this API gets right is that it will generate a random IV for you if you don't specify one, which is usually what you want. But you have to kind of know then that after you've initialized it, you have to call this getIV method to get it. And you have to know that you have to write that out with your ciphertext, and when you read it back in, you have to read that back in. So there's a bunch of details you just kind of have to know. And the same with decrypting here. I have to know when I'm reading it in that this IV, I've written it out at the start, and I either have to know that Galois counter mode takes a 12-byte IV, so read 12 bytes, or I have to somehow encode that into my message. And then read the rest. And I've got things here like this. When I'm initializing the cipher at the bottom, there's this GCM parameter spec, which is very specific to this mode. You don't use it in any others. And there's some things I need to know, like there's this 128 magic number in there, which is the number of bits in the authentication tag. And with GCM, you never want to use anything other than 128 bits. But the library makes you specify it. Because if you specify a shorter one, GCM mode has a real security issue with short tags, that it doesn't provide the level of security that you'd assume it does. Another kind of pitfall there is that that's given in bits, and a really common error in old style crypto libraries is a confusion between bits and bytes. So if you think that's bytes and you put 16 in there, you're going to get a 16-bit authentication tag, which is trivially brute forceable in microseconds. There was an interesting bug in a Java crypto library called Bouncy Castle a few years ago where they made exactly this mistake. They had a key size field that was supposed to be in bits, and somebody passed in 16 instead of 128, and then again they were generating keys for encrypting a file which were only 16 bits in size. Another pitfall here is that when I initialize the cipher here, I have to initialize it in decrypt mode. But a quirk of GCM or lots of these modes is that encryption and decryption is the same operation. So if I accidentally copy and paste this code, because it's lots of code from the encryption thing, and I leave that saying encrypt mode there, it will still work. It will still decrypt all of my data, but what it won't do is verify the authentication tag on the end of that data. And so I'll have no idea whether this data has been tampered with. What I would get on the end is some kind of random garbage right on the end of my thing, but as an attacker I can sometimes make that look a bit like a comment or something else that's going to be ignored by the application. So there's these kind of things which are kind of easy mistakes to make, and you might not even pick them up in code review, but can have devastating consequences on the security of your system. So a few kind of summary of some of those points about these old style cryptography libraries. They're built around these very general abstractions. So back when we were designing these libraries, we didn't really know, that authenticated encryption was the way you were going to do encryption, say. Right? We were still working these things out. And so they were built around very general abstractions with with different primitives providing very different security properties. And this is the same with the Java API. It's the same for things like OpenSSL and other kind of libraries of the time. There's a huge number of different choices of algorithms. So particularly with the Java thing, you don't just get the built-in algorithms in the library, but it's a pluggable architecture. So you can just load other third-party libraries which add new algorithms. And so you get stuff like commonly used libraries, which are kind of developed by people who are kind of cryptography enthusiasts. And so you get some algorithms in there that are just kind of random stuff that was presented at a conference years ago and somebody liked it and implemented it. And there's a general assumption with these libraries that the user is an expert and they know all these pitfalls and they'll take care of it themselves. So it's very easy to make mistakes. So modern cryptography libraries like Tink are designed to kind of steer you away from these pitfalls and provide a way that you can implement this code within your applications without undermining the security. Because often it's not the crypto that gets broken in applications, it's some kind of mistake in the implementation that causes the issue. And the reason why there's a picture of these kind of salt fields here is probably the first modern cryptography library in this standard was something called NaCl, which is NaCl. Most people pronounce it as NaCl, but obviously NaCl is sodium chloride, and so it's referred to as the SALT library. It actually stands for the Networking and Cryptography Library. So that was developed by a cryptographer known as Daniel Bernstein, who's very famous in the area, if you know at all about cryptography. He's developed lots of cryptographic algorithms, but he also developed this library, which takes a very opinionated, high-level approach to cryptography. So you have a bunch of operations like encrypt this data with this secret key, and it has a hard-coded algorithm that he has chosen as an expert cryptographer that does that for you. Or there's another one where you can say, I've got Bob's public key and here's mine, Alice's private key. Do some magic to create a shared secret between us and then encrypt some files to them. So they have kind of well-defined security goals, but there's one algorithm, and that's the Dan Bernstein approved algorithm. And if you need to do something else, you're kind of out of luck. Which often as developers, unfortunately, we do have to do something else, because we're not just encrypting a file that we're going to read later. We're encrypting, we have to interoperate with other systems. So we're encrypting a file we're going to send to some other system. We're implementing a standard like OpenID Connect, which has, you know, in the specifications it says these are the algorithms you use, right? And if those are not the algorithms that your library implements, then you're back to using one of these old style, super flexible crypto libraries. So Tink tries to sit in the middle ground where it provides lots of different algorithms and lots of things that are kind of standards, but it also has well-defined interfaces that are hard to misuse. And there's a few other libraries as well that have been developed that offer a similar thing. So this is the equivalent code for encrypting and decrypting a small file in Tink. As you can see, I can fit both of the code samples on one slide now, so it's obviously a lot smaller. But there's a lot of details that I don't have to worry about here. So the whole notion of an IV doesn't appear in this code at all. I don't need to even know that that exists as a thing. Because Tink will just generate one for you randomly and will prepend it onto the ciphertext automatically. And then when you read it back in, it knows to read that in as well. It doesn't even mention the algorithm here, so I don't even have to know what algorithm to use. In fact, we'll get onto a little bit later how you can choose which algorithms to use. And also, rather than having this general cipher abstraction, I have this specific AEAD abstraction, and it's a typed interface that says every implementation of this interface gives me authenticated encryption with associated data. And in fact, if you go to Tink's documentation, they provide further guarantees. You know, you will have this minimum strength against key recovery attacks, this minimum strength against authentication forgeries and things like that. So as somebody like me who reviews cryptographic code quite often for my living, this is great to come in and go, right, I can see that type being used there. I know exactly what security properties I'm getting and which ones I'm not. So it's really useful in that way. And there's other things, before I said about, if I accidentally leave it in encrypt mode rather than decrypt mode, that it will just kind of silently work. Well, the same thing won't happen here because it generates that random IV for you as part of the encryption. If I accidentally call encrypt rather than decrypt, what I'll get back is garbage, just random data, and so my application will fail. So again, this is another kind of design principle in Tink, that those kind of accidental errors fail noisily in ways that you're not likely to overlook. So some design principles in Tink then. So each primitive operation has its own interface. So in languages that are well typed, you have a typed interface. And all implementations of that interface achieve the same security goal. So you can chop and change between those algorithms and you're getting that same security goal, which is not the case with using the Java low-level API, where you change the algorithm and you might get completely different security properties. And different algorithm choices may have different performance properties, but they all meet a baseline level of security. So these are some of the algorithms that are supported. You can people like me who are into crypto can kind of geek out on like picking between different ones and the different trade-offs between them. But generally with Tink, it's nice is that they're all basically secure. There are some things like AES-GCM, Galois counter mode, we saw before. It kind of has this thing that it's fragile. If you repeat one of those nonces, numbers used once, then it fails really quite catastrophically. You can recover the authentication key and forge messages, and you can also recover information about the messages that are encrypted. But again, because Tink is hiding that for you and generating random ones, you're much less likely to accidentally encounter that. So even though it has that corner case, it's kind of solved for you. If you're encrypting loads of messages, then there's even kind of interesting things like AES-GCM Civ there, which was developed by Google, which is a kind of more robust version of GCM. It's kind of, I think it's a bit slower during encryption, but it runs at pretty much the same speed during decryption. But if you reuse one of those nonces, almost nothing fails. The only thing you can tell is if the same message has been encrypted twice with the same key. So you've got all these trade-offs, and you as an engineer can look at that and go, right, I'm going to use this algorithm, that algorithm, or maybe the spec tells me I need to use this particular algorithm. But you can kind of relax that it doesn't really matter which one you choose because they're all basically secure. So that's the same thing again. So Tink has this design principle that it supports lots of different algorithms, but they all implement the same security goal. So you're kind of safe in choosing between them. So now we get on to what is probably one of the most interesting parts of Tink. So there's this nice quote from Leah Kistner, who used to work at Google, who said at the time that cryptography is a tool for turning lots of different problems into key management problems, right? So, you can add cryptography to a solution and you get a nice secure solution, but now you have the problem of managing your keys. And so Tink also provides some nice solutions for that. And this is in a thing that they call Keysets. So if you were paying attention in those previous code examples, you might have noticed that rather than passing in a single key into operations, I'm passing around something called a keyset. And that is to support a notion called cryptographic agility, which is basically the idea that the algorithms that we consider secure change over time. So we used to think that like MD5 and things like that were secure as hash functions. Now they're kind of trivial to break. So there's a nice hacker magazine that comes out as a PDF called POC or GTFO. I won't say what that means on the recording. But they have a nice trick they've done on lots of their things where they have the PDF, the front cover of the PDF has the MD5 of the PDF like in the image on the PDF. So they've managed to calculate the MD5 hash of that PDF that contains its own hash kind of thing. So it's kind of a nice little thing. But that's how broken MD5 is now, that you can do that reasonably cheaply. But back in the 90s, you might have thought MD5 was a secure hash function to use. So that kind of changes over time. But there are lots of kind of dangerous ways to do cryptographic agility. So There's a standard called the JSON Web Token, or JWT standard. That is the official pronunciation of JWT, is JWT. It has what we'd call in-band negotiation of algorithms. So there is, when you have your JWT, it's signed with some kind of signature algorithm or a message authentication code. And then there's a header on the JWT which has an algorithm field, an ALG field, that says which algorithm was used. And the problem with that is that an attacker can then mess with that algorithm field and maybe get you to interpret the security in a different way. And in particular, one particularly bad case is that the JWT standards, for reasons that are not entirely clear, supports this algorithm called none, which disables all security. It means it's completely unsigned, it's called an unsecured JWT. So if you're an attacker and you've got, say, some system that's using JWTs for its, authentication, you can just take that JWT, which may be signed with RSA or something like that, and you can just change the algorithm to none and then change the username to like admin or something like that and send it in, and maybe, and in fact quite likely in some cases, the library will just go, oh well, this is a perfectly valid JWT, it's got no signature on it, but it doesn't need one because it's algorithm none, and then you're logged in as admin. And this was such a common problem that somebody set up a website which is called something like how many days since the last JWT alg none vulnerability. When I looked the other day, it was up to like 240 odd days, which is pretty good for this website. There's usually been several a year since the JWT specs came out. So this is kind of a problem, right? So this is kind of, they're trying to do algorithm agility by communicating the algorithm in the message. But this violates something that's come to be known as the cryptographic doom principle, which was first kind of said by Moxie Marlinspike, who's the cryptographer who co-developed the Signal protocol, which is used by like WhatsApp and things now to secure their things. And he said basically that if you have to perform any kind of operation really on a message before you've authenticated that message, then it will somehow inevitably lead to doom. And he went through various cases in like old versions of TLS and SSH and things like that where this happened, but it's basically the same idea with this JWT. So you have to read that header and trust that algorithm value before you've verified any kind of signature on that message to determine whether it's trustworthy. And so you've got a kind of chicken and egg situation. A more subtle version of this attack is known as a confused deputy. This was discovered by a security researcher who found that, let's say your JWTs were signed with RSA, so you use a private key to sign the JWT and then you use a public key to verify it. Well, he found that you could change this algorithm to a symmetric secret key algorithm, in this case HMAC with SHA-256. And then what you could do is you could take the bytes of the public key, which is publicly available, typically on an endpoint on the website, treat it as if it was a secret key and sign it. And loads of JWT libraries will also accept that and just go, okay, well, I'm going to verify this with the public key. Let's take the bytes of that public key and verify it as if it was a shared secret. And so that meant, again, that you could forge signatures by just confusing the library about which algorithm to use with which key. And this is an example of what we call a confused deputy attack in security. So you're confusing the library about which algorithm to use with which key and having devastating consequences. So one way to kind of get out of this, which is a way that some people have done, is just say cryptographic agility is just a terrible idea, we shouldn't do it. So there are some protocols now which have been developed where they're just like, there is one algorithm that you use, and if that algorithm ever turns out to have weaknesses, we'll just do a version 2 of the protocol and everyone will have to upgrade all at once. But this kind of goes against, so Tink is developed by Google, and Google have these software engineering design principles that they follow. They wrote this great book. And one of their key principles there is that all software changes over time. Requirements change, algorithms change, standards change, and that you can't be re-engineering and re-architecting your software every time some change happens. And so they have to be designed to handle change. And so the way that Tink comes up with this is a process that I refer to as key-driven cryptographic agility, which is the idea that rather than trying to negotiate the algorithm in band in the message, you associate the algorithm with your key and you store that in the metadata that's along with your key. So you're storing your key somewhere securely on your server in a key management system or something like that, and you have some metadata alongside that key that says, right, this is an RSA private key. It's used for RSA signatures with whatever padding scheme and whatever else. And so the way they do this is they have this idea of a key set. And so a key set is what it says. It's a set of keys that are all designed for one purpose. So say you're going to be signing OpenID Connect ID tokens or something like that. You have a key set that's just used for that purpose. And within that key set, you can have multiple keys. And each key has associated with it some metadata. So it has a key ID, which is a 32-bit integer, which is unique within that key set. And it has some kind of algorithm or type that says what algorithm it's used for. So here we've got some keys for encryption. And we've got two of them are using AES in Galois counter mode. And then we've got a new one we've added that's using this char-char-20 poly 1305 algorithm. And one of those keys is marked as the primary key. So that means whenever we're producing a message, so if we're encrypting a message that we're going to send to somebody else, or we're signing something that we're going to give to somebody else, then the primary key is what gets used. And that also then determines the algorithm. So when on those previous slides, when I was showing how you do encryption in Tink, and I was saying there's no algorithm, this is how it works it out. So it says, right, you're encrypting something, so I'm going to use the primary key from your key set, and that has this algorithm char-char-20, or char-poly as we refer to it, because that's a mouthful. And so that's the algorithm it's going to use, and it's going to encrypt with that. And this is how you get safe cryptographic agility, because to move to a new algorithm, you add a new key to your key set with the new algorithm, and then you rotate your keys to move to the new key. And that kind of solves these two problems. One is key rotation, which is something you should do. So cryptographic keys have a lifetime. There's a safe number of messages you can encrypt with a key, for example, and then you have to move to another one. So by forcing you to use key sets, Tink makes it easy to move to new algorithms, and it also makes it easy to change your keys all the time. So the reason why the other keys are still in there is when you think about when you're consuming a message that you've received back. So let's say you're decrypting a file that you encrypted ages ago. You still want the key that you encrypted with it originally. You might have moved to a new key and a new algorithm, but you still want to be able to decrypt that old one. So those keys can stay around for a while. So the primary key gets used for new stuff, but those keys are still around for old stuff. And same for like verifying signatures and things like that. So by default, the Tink primitives, when they write something out, they add a little header to the output. So that includes this key ID and includes anything like this random IV that it's generated and stuff like that. So that's then, when it reads it in, it knows which key in your key set to use without having to just try them all one at a time. There are also raw variants. So if you've got to implement some kind of spec that says the exact format that messages have to take, then you can use these raw variants, and then you won't get this key ID written out. But in that case, you either have to communicate it in some other way, or it will fall back to just trying every key in the key set, which is it's not insecure, but it is potentially slower. So the way you create a key set is you can either, there's programmatic APIs you can use, or they have this nice little command line utility that you can use to create them. If you've ever used something like Key tool in Java, which generates their kind of key files, then it's a similar kind of process. So you initially create a key set, and you provide this key template, which is the algorithm. And what that's going to do is, a key set can never be empty. There's got to always be at least one key in it. So when you create the key set, you're not saying all the keys forever are going to be this AES GCM mode, just the first key. So it will generate a first initial key for you using that template, and it will mark that as the primary key. They support a couple of formats. So they support this JSON format, and they support like a binary format. But this key set that I'm creating here is completely unencrypted. So it's just plain text bytes sitting on on disk, so that's kind of really only secure for test cases and things like that, where these keys are not really going to be used for anything important. I'll come back soon to encryption, because Tink has a very opinionated view of how to encrypt key sets. And then the way you use it, again, you just kind of read in your data using whatever I/O your thing does, and then they've just got some primitives where you can just parse that into a key set. And if it's encrypted, there's a way you can pass in the decryption keys. This insecure secret key access bit we'll come back to in later. That's again another little nice thing for people like me who do code reviews, but I'll come back to that later. So within a key set, keys have a life cycle, and the key sets have a life cycle. So you create an initial key set, and it has this one key in it, and then if you want to move to a new algorithm or rotate your keys, then you can add a key, and then at some point you can then promote that key to become the new primary key in your key set. The reason those are two separate operations is there's often a step in between where, let's say you're signing OpenID Connect ID tokens, you add a new key, which is say elliptic curve public-private key pair. You then have to go and distribute that public key to all your relying parties, right? If you just started signing with a new key and they haven't got the public key, they're going to reject all your signatures. So this is kind of a two-step process where you create the key and add it to your key set, then you distribute the public key or wait for them to come and fetch it from your website or whatever. And then once you're satisfied that everyone's got it, then you promote it and start using it as your primary key. You can later on disable a key. So if you think, right, I'm done, I'm never going to use that key again, you can disable it. That it still keeps it in the key set, so the key material's still there. So if you find out you've made a mistake, you can re-enable it later, and you can even re-promote it back to the primary key if you want. And when you're totally happy that this key is really never ever going to be used again, you can delete it, in which case the key material is lost forever then, unless you backed it up. Okay, so now we'll get on to talking about encrypted key sets and how Tink handles those. And as I said, it takes a very opinionated approach, which is that you should be using something called a key management system. So if you're used to things like Java key stores or OpenSSL key files or OpenSSH key files, you might be thinking, why not just use like a password to encrypt this file? Which is what a lot of these things do. So when you create a key store in Java, you supply a password, it does some password-based encryption and encrypts that file for you. And that's fine for things like your OpenSSH keys on your own machine. You know, you go and try and SSH into something, or normally for me these days, it's when I'm trying to push something to GitHub and it prompts me for my SSH key password. And then I, as a user, I'm there and I can interactively type that in. But Google are not building Tink for those kind of interactive use cases. What Google build are web apps. And so they have servers running somewhere, and they're running at scale, and those servers are starting and stopping all the time, and they're scaling them and adding new instances and so on. And you can't just have some guy running around typing in passwords into machines every time they start up. It's just not going to work that way. And so you have to have some way for this to uninteractively start up. And so typically what ends up happening if you have, if you're using password-based encryption of your keys, is that you get this encrypted key file, this key store file that you put on your web server, and then right next to it you have the unencrypted password in another file. And from a threat modeling point of view, this makes no sense at all, because there's no way that an attacker would be able to get access to that encrypted key store and wouldn't always already have access to the unencrypted key store password next to it. And there's various things people try and do, like maybe putting the password in an environment variable or stuff like that, but they're generally all fairly insecure. The other problem with these kind of passwords is that often that password then just gets, it's the responsibility of the developers to manage it in some way. So it often gets checked up into Git next to the code, or it gets passed around on like Slack channels in the internal chat app and things. And as the kind of information security team in your organization have no idea where this password is, who's had access to it, or anything like that. And so Tink takes the the decision that all encrypted key sets are going to be managed via a key management system, or KMS. So most cloud service providers have these, and basically a KMS is a service that does crypto on your behalf. So it stores keys in its secure storage, and that might be like hardware security modules or some kind of hardened storage. And then you call it and say, you don't say, give me the key, you say, can you encrypt this bit of data with this key, or can you sign this thing with this key? And it gives you back. So the way that Tink encrypted key sets work is that it generates a random data encryption key, DEC, and encrypts the file, the key set file, with that. And then you call the KMS and say, right, can you encrypt that DEC with your key encryption key? This is called envelope encryption, usually. And so, and then what you get back is this encrypted data encryption key that you tack onto the front of your key set. And now when your web app starts up, it reads that encrypted decryption key, it calls the key management service and says, can you decrypt that? And it says yes, and gets back the decrypted key, and then it uses that to decrypt the rest of the key set. So this provides a couple of advantages. One is against that idea of passwords being like passed around in Slack channels and put into Git and stuff. So now you have a centralized key management service that has lots of nice audit logs, and your InfoSec team can set access control policies and all kinds of things, and that makes them very happy. And the other thing you might be thinking is, well, this web app still has to have some kind of credentials to connect to the KMS, and those are just sitting in plain text on the disk. So right, can't an attacker just read those somehow and then just connect to the KMS directly and start decrypting things? But usually it's a bit more complicated than that in cloud. I'm not going to go too much into the details of cloud credential management, but usually what's sitting on the disk is not the actual credentials, but some kind of limited access token, and you have to call some kind of local metadata service to swap that for the actual KMS credentials. And you can do things like locking down the KMS to only be accessible from that network and things like that. So there's this kind of additional hardening you can do beyond just having a file on disk. So Tink supports a bunch of different KMSs at this point. So obviously they support Google's own KMS. They're happy to sell you to that. They support Amazon's KMS in AWS. They support HashiCorp Vault, which is a well-known kind of open source key management and secrets storage vault. And Tink also runs on mobile devices. So they have, like, the Java version runs on Android, and the Objective-C version will run on iOS. And on those platforms, it will use the device's local secure keychain or key store to store keys. So you can have things, on your phone where you've got to do Touch ID or Face ID to unlock those keys and then use. So you've got extra levels of security there. So again, you can use this Tink command line utility to generate an encrypted key set, and it's pretty much the same as before, except you now pass in this master key URI where you tell it which KMS, and there's a particular URI format for these different KMS that specifies what region and what project and what keyring and stuff to use. It knows how to, if you're running this in Google Compute Engine, for example, there will be default service account credentials associated with that environment, and it knows how to automatically pick those up. So it's kind of, if you're running in those environments, or you've installed like the G-Cloud SDK on your laptop, it can automatically pick those up. So it kind of then makes that, this is pretty much as easy as creating an unencrypted one. Or you can specify the credentials manually if you need to. So you might be thinking, well, if I've got this key management service that does crypto for me, it's way more secure than doing stuff locally. Why not just use that for all my crypto? Right? Why use Tink when I can just use this KMS? And Tink does have a way that you can use your KMS with that envelope encryption if you want to. But there's kind of three reasons why you wouldn't use the KMS directly. So one is cost, in that when you make calls to the KMS, they charge you money for those API calls. It's typically not a lot. I think Google KMS is charged per 100,000 API calls, so you'd have to be doing quite a lot of crypto to run up a huge bill. But for example, if that crypto is on your front of your web application or something that's exposed to the internet, then what's the risk of somebody hitting you with like a denial of service attack and running up a massive bill because you're making crypto requests on every single request? The other thing is kind of performance or latency, which is that the KMS is over the network. So cryptography done locally on most modern processors is really fast. So CPUs have hardware acceleration for things like AES now, and they're really fast. Calling out to the KMS, you're going to make a network round trip. So even if the KMS is super fast, you've got some latency overhead, and you often get a lot of variability of that latency as well. So you can get variations in the response time from that KMS, especially if you ever use a KMS from a different availability zone, which I've done accidentally in the past. That latency can get quite high. And finally, so the final reason then is flexibility, which is that a KMS typically only supports a few algorithms, and if those are not the algorithms you want, then you're out of luck. And also they tend to have quite small limits on the amount of data that you can encrypt or sign or whatever in a single message. So again, using Tink in this envelope encryption way, you kind of get the benefits of the KMS in that your keys are secured via it, but once you've started up and your system has decrypted its keys, everything else runs locally then. So you also don't have to worry about the KMS being available for the whole lifetime of your app running. So skipping back a bit, I pointed out that when we were loading those key sets, there was this insecure secret key access class that we had to use. And that is really just a marker, and it's there for another key design goal of Tink, which is auditability. The idea that crypto code is often very sensitive code in your app, and you need to be able to review that. So people like me come in, look at your code, pay to kind of do a code review, and we want to find the bits that are risky. And anywhere you're accessing raw key material, so either you're kind of loading keys, saving keys, potentially manipulating keys, those are potentially risky areas where you might be doing something, you might be leaking key material. And so all of Tink's APIs that do that require you to pass in an instance of this insecure secret key object access class. And that's just a singleton. It has no functionality at all. It's just a kind of marker that you have to provide. And it means for somebody like me going in, I can just grep for that class name across your source code, and I immediately know these are all the bits where you're doing something potentially a bit risky. And so I can concentrate my effort on those bits. So that's a nice thing. Again, they're kind of experienced with doing those kind of code reviews themselves, and so they've added these features. Okay, so that's kind of key management covered. Use a KMS basically. So now we're going to look at some of the other primitives that Tink provides. So before we talked about encrypting quite small files, and the AEAD primitive that we were using, it required you to pass all of the data you want to encrypt as an argument to that method, which means that all that data has to fit in memory. So that's fine for small config files and things like that, but if you're trying to encrypt like a massive movie or like a huge multi-gigabyte database or something like that, that's not going to cut it. So Java's old school API has this thing called the cipher input stream and cipher output stream that you can use for this kind of streaming. So we can just kind of wrap them around these I/O streams with our cipher, and then it will kind of transparently encrypt or decrypt stuff on the fly as we're reading it. And then we can just kind of process stuff in chunks. Maybe we've got a buffer here of like 1 megabyte, and we're reading that in and we're processing things as we're going. There's a couple of problems with this. One is that this API predates really the idea of authenticated encryption. So it has no way at all to say that an authentication failure occurred other than throwing this very generic I/O exception. And if you've ever written or looked at Java source code in the wild, what most people do with I/O exceptions is what this is doing up here, which is just catch them, log them, and ignore them, because nobody really knows what to do with I/O exceptions apart from try it again. So the other issue as well is that authentication tag that is used to verify it is just written once at the end of the file. So we've gone through and processed the entire file, and it's only at the very end that we're going to check that authentication tag, which means that this because we're processing as we're going in these 1 megabyte chunks, we might have done loads of stuff. You know, we might have committed stuff to databases, we might have sent messages to other systems or sent emails and things like that. And then we get to the end and go, oh no, that all turned out to be tampered with. What do I do now? And suddenly you've got a major incident now, and you've got to kind of manually roll back all this stuff or have some kind of way of recovering. And this is a general problem referred to as releasing unverified plain text. So when you're doing authenticated encryption, if you're releasing plain text as you're decrypting it before you've verified whether it's authentic, that's this problem. And so the solution that Tink uses is what's called a streaming AEAD primitive, authenticated encryption primitive. And this diagram's a little bit complicated, but basically the idea is that we split up our message into fixed-sized chunks, or maybe application-specific chunks, like say 1 megabyte, and then we encrypt them all individually with our AEAD, and so we get a tag every 1 megabyte or whatever that we can verify. Now that obviously adds some overhead, so you know, but these tags are like 16 bytes, so 16 bytes every 1 megabyte, and obviously the bigger the chunks, the lower the overhead. Now if we just did that in a kind of naive way, then there'd be a lot of attacks that attackers could do. For instance, they could reorder those chunks on the wire, or they could throw some of them away or duplicate them, or they could just truncate the stream at some point after a thing. So there's this design that was come up with by cryptographers, Phil Rogaway and his group, where you basically encode some stuff into the nonce, into the IV that you use for each of these chunks. So you have a segment counter which says which chunk you are, and then you have a kind of bit at the end, a stop bit that says whether you're the last chunk or not. And there's a kind of nice proof of correctness that solves these problems. And so Tink then has this streaming AEAD primitive. Again, we get our key set, and then we say, oh, give me a streaming AEAD, and it will go through and find an algorithm, and then we can create this new encrypting or decrypting stream. And then it pretty much works like the cipher input stream, except it's safe. So when you're saying, oh, give me a megabyte of data or 8 kilobytes, say, of data with this read thing, what it's going to do is read the whole of the next chunk, next segment from the input stream. It's going to verify the authentication tag over that thing, and only when it's satisfied that it's authentic and not been tampered with is it going to actually decrypt it and copy some of that data into your buffer, and then buffer the rest in memory. So whenever you're processing data here, you're never processing unverified plain text. It's always verified the tag at that point. And the worst thing that can happen is you get halfway through and then there's an authentication failure, but you know that no previous data was tampered with at that point. You know that chunk failed authentication, but you haven't processed any of the data in that chunk yet. So it's much safer. You're never processing unauthenticated plain text. To keep compatibility with the cipher input stream, it still just throws this generic IO exception. But again, it doesn't matter if you just log that because no damage has actually occurred. You've not actually processed any bad data. So again, they just provide a couple of algorithms here. This is kind of quite a new cryptographic primitive, so there's not a huge amount of standards that kind of specify these things. They just have a couple of ones. They're both basically fine in the way that Tink uses them, so you can pick whichever you want. The GCM one is by far the fastest, so that's generally what most people would choose. So that's kind of encryption, or symmetric encryption. So we look now at kind of message authentication and digital signatures. So these are pretty straightforward. So message authentication, or a MAC message authentication code, is basically like the authenticated encryption we saw before, but without the encryption. So it just authenticates. So you get data origin authentication or message authentication. And this is dead simple in Tink. So to compute a MAC tag over some data, you get a MAC instance from your key set, and then you just compute the MAC over the tag, and it returns this fixed size tag, which is typically like 128 bits or something like that. And then to verify it, you do the same, but you call this verify MAC method, and you pass it in the tag and the data, and it's going to recompute that MAC tag and check in constant time that they're the same. So one interesting thing about this API, though, is this verify method at the bottom doesn't return anything. So normally in APIs, it would return a Boolean which says whether it's success or failure. But it's quite easy to just ignore that result, and people have in the past just ignored that. So what Tink does instead in their rationale of always failing noisily is it doesn't return anything, but it throws an exception if it doesn't match. So again, you can't fail to do that. Again, they provide a couple of algorithms. Almost everyone uses HMAC, despite the fact it's kind of slowish for this kind of thing. There's this AES CMAC, which is faster because it uses AES, and AES is hardware accelerated pretty much everywhere these days. But almost nobody uses AES CMAC out of particular AEAD constructions. They also support public key signing and encryption. They're different primitives to the MAC, so those kind of things have different security goals, so they're not the same. So you have a public key sign where you call your primitive, and that's going to use the private key to sign the data. And then you have a public key verifier here, which is going to use the public key and not the private key. And in fact, I think it may throw an exception if you have private key material in that key set. And again, it uses the same thing, that this verify method at the bottom will throw an exception if the signature doesn't match, and otherwise it doesn't return anything. It supports all the kind of modern algorithms you'd expect it to support, so elliptic curve, digital signatures. AEAD 25519 is a Daniel Bernstein thing. It's very fast, kind of good security margin, but still kind of slowly being adopted. And it supports good old RSA signatures as well. So now we're going to talk a little bit about JSON Web Tokens, JWTs. So we talked a little bit before about this algorithm header and how error prone it was. So JWTs are an increasingly important standard though. They are used everywhere now. They're kind of the go-to way that people do application level cryptography now. They're in loads of standards now, things like OpenID Connect, OAuth, banking standards, all kinds of things they're being used now. So they are, like them or loathe them, they are very widespread. Lots of cryptography and security people like me don't like them because they're a bit like those old school crypto libraries in that they give you lots of options which have subtle security property differences, and you're kind of expected to choose between them. But they are extremely widespread. So Tink took the unusual step, and this is the only kind of application level thing that they've included, and they directly now include a JWT library within Tink that is designed by them to kind of avoid some of these common problems. So this is kind of the code in Tink for creating a JWT. So first of all, you create this thing called a raw JWT. So if you're not familiar with JWTs, JWTs have a JSON object in the start, which is called a JWT claim set, which has a bunch of claims about typically a user who's logged in. So it says who they are, maybe their email address and things like that. And then it also has a bunch of things which are still called claims, but they're really more kind of conditions or restrictions on use. So for example, they have things like an expiration time, which says, you know, it can only be used up until this point in time, and then it's no longer considered valid. Or you can have something called an audience on it, which says, you know, these are the servers that I'm going to send this JWT to, and if you're not in that list, then you shouldn't get it. And so Tink provides this kind of builder pattern where you can create those claim sets, and it there's things like if you don't set an expiration, then by default it will reject it and say, well, maybe you should, and you have to call a kind of, you know, I definitely don't want an expiration time method if you don't want that. And this raw JWT that it returns, you can't really do anything with that. The only thing you can do with it is pass it to one of these JWT signers at the bottom. So you can't convert it into a string in any way, you can't introspect the values in it, and so the only thing you can do with it is sign it and get back an actual JWT. So again, it's kind of like steering you towards not accidentally using this thing as if it had some security. And so you call this primitive, and then you compute the MAC, and it returns it. So this is using a a HMAC-based algorithm on this. And it doesn't let you, so JWTs have this header as well, which has all kinds of options and things you can pass in. We talked about the algorithm before. And that header section is probably, in my opinion, for a standard, it's kind of the most footguns per square meter of almost any standard. There's so many of the things that you can specify in that header have security vulnerabilities. And so Tink just kind of hides all of that from you, and it sets those headers automatically, the ones that it needs to do for the standards. And the only one it allows you to set is this thing called a type header at the bottom. And this comes from, I believe last year there was a new specification issued called the JWT Security Best Common Practices document from the IETF. I was involved with kind of some of the review of that, and that gives, you know, a bunch of lessons learned over the years with JSON Web Tokens in practice, and here's a bunch of things where people have made mistakes and things to avoid. And one of the recommendations that made is that you should use what's called strongly typed JWTs. So the idea is that because JWTs are becoming so ubiquitous, you now have apps that are using them for lots of different things. Like they may be creating ID tokens, they may be using them for some other purpose as well. And they often have overlapping claims, and people end up using the same keys for them because it's easy to use the same keys. And so you can have situations where a JWT signed for one purpose, you can replay it against a totally different endpoint for something else, and it happens to be accepted as valid. And so you get these kind of interesting type confusion vulnerabilities where it's getting confused about what's for what. And so by setting this type header, you're saying explicitly what this JWT is for. And then when you're receiving the JWTs, you're supposed to check this header and say, you know, is that for the purpose I wanted this JWT for? And so that's the only header they allow you to set. And they also will automatically verify that header. So if you don't set this header when you're verifying in here, so this is the code for verification, if you don't call this expect type header and tell it which header to expect, and the JWT comes in and it's got one of these type headers on it, then it will reject the JWT. So it's kind of failing safe again. So again, for the validation purposes, you build this kind of JWT validator which says what your expectations are for how the various claims should be set. For some things like the time base, so there's expiration and not before time in a JWT. Those it will check automatically. And you can also then give it this thing called a clock skew, where you say, you know, these JWTs are being created by clients. Those clients may not have synchronized clocks, so their clocks might be out compared to my server clock. So you can say, well, you know, we're going to respect this expiration time plus or minus 2 minutes or something like that. In fact, you generally shouldn't hard code this value. The best thing to do is to kind of observe the clock skew when clients authenticate or whatever, and then record that for each client, and then you kind of can have a narrower thing, because if you have just a single value, then the pressure is on over time for that to just get larger and larger and larger to accommodate more and more clients. So again, we're using a message authentication code based JWT algorithm, and so we get this JWT verifier from a key set, and then we verify and decode. And that's all as one step. So what it's going to do, it's going to verify the HMAC tag on that JWT. It's then going to validate all of the claims and things in that JWT. And only when all those are satisfied is it going to return this thing called a verified JWT. So again, it's returning a specific type that says this has been verified. And that verified JWT is the only class that actually allows you to access the data in the JWT. So the rest of your application then can just accept one of these verified JWT types throughout your code, and you know that you can't possibly have got that without having checked the signature. So there's a nice article somebody wrote a few years ago called Parse Not Validate, and the idea is to use this kind of pattern. So rather than having some check code that checks a signature or whatever and then throws an exception or returns a Boolean, you actually transform your input into some kind of verified output that has a specific type that guarantees some security properties. So that was secret key message authentication codes. They have the same for public key signed JWTs. So again, similar to public key signatures we looked at earlier, there's separate primitives for this. So there's a public key sign, which is actually going to use the private key. There's a public key verify thing. And again, it has this thing that you have to use your keyset handle when you're getting this public key verify, has to only have public keys in it. And if not, it will throw an exception. And the idea of that is, you know, you're using these public key signatures. Normally you're signing on one system and then you're distributing the public key to other systems, and you want them to be able to verify but not sign. So you don't want to be accidentally sending them the private keys. And so there's this kind of extra check that there's no private keys in there, just to stop that happening. It supports basically all the algorithms that were in the original specifications, apart from none. It very much does not support none. So you've got the symmetric HMAC algorithms, ECDSA, RSA, and the various variants of RSA. It doesn't at the moment support encrypted JWTs. There's a whole part of the standard around encryption. They don't support that at the moment, and they don't support these AEAD DSA signatures, which are kind of newer. But they do support, I mean, this is in practice what everyone is using when they're using JWTs, so it does support the use cases that most people are using at the moment. Finally, there's another part of the JWT standards called JSON web keys, and this is often used in these systems where you can publish your public keys in a standard JSON format and put it on your website on a HTTPS thing, and then your clients can just go and download your keys from there, and it kind of, the trust is then bootstrapped by the web PKI, which if you talk to some people is perhaps not a good idea, but it's a very widespread thing now. And so Tink, as you might expect, has a way to convert your keyset handle into a JSON web key set, which looks like this. So you have a keys object here with an array of then keys in it. And those keys, again, can have loads of optional constraints added to them, and Tink kind of sets all the good ones. So for example, this algorithm field here says which signature algorithm is going to be used with this key. So again, it's that key-driven cryptographic agility, that they don't want you looking at the message to find out the algorithm. They want you looking at the key to find out the algorithm. And it says, you know, what can be used for. It's just used for signature verifying. You can't use this for encryption or anything like that. And this key ID here, which is kind of base 64 encoded, is that 32-bit keyset key ID. So it kind of all just kind of links up in a nice way. So moving on from JSON Web Tokens, we're now going to look at a couple more little bits left in the Tink library. So one of the things it does support is public key encryption, even though it doesn't support it for JWTs, it supports it for general purposes. And the way you do public key encryption, it's not just the same as symmetric key encryption where you just encrypt something and decrypt something. What you do in practice is something called hybrid encryption. So if you've got a public key encryption algorithm like RSA, you don't just use RSA to encrypt your whole message, because RSA is at least an order of magnitude slower than symmetric crypto, and there's a limit to how much you can encrypt. So if you've got, say, a 2048-bit RSA key, you can only encrypt up to 2048 bits. So what you do, or what you used to do in the old days, was something called hybrid encryption, which is a mix of symmetric and public key crypto. And what you would do is generate a random, say, AES key, a symmetric crypto for each message, use that to encrypt the message with something like AES in Galois counter mode. And then you'd encrypt that random data encryption key with RSA. So that's the only bit that gets encrypted with RSA. You'd then send that to Bob. Bob would use his private key to decrypt that AES data encryption key, and then could decrypt the rest of the message with AES. So that works for RSA, but it doesn't work for basically anything that isn't RSA. And so there's lots of other public key encryption systems we'd like to use that don't look like RSA. So for example, elliptic curve cryptography systems don't work like that. And also in the future, we're looking at things like post-quantum cryptography coming up. So we've got this idea that there might soon be quantum computers being developed that can break all kinds of existing public key encryption algorithms, including RSA and elliptic curves. And so we need to move to new algorithms that are secure against quantum computers. And none of those work like RSA either, as far as I'm aware. And so instead what we use is something called the chem-dem paradigm for hybrid encryption. So a chem is a key encapsulation mechanism and a dem is a data encapsulation mechanism. The dem here is it's basically an AEAD that we saw before, so it is some symmetric authenticated encryption mode. Now the difference from RSA here is that this chem, you don't generate your own AES key and then ask it to encrypt it. What you do is you call this encapsulate method and it spits out a new fresh random data encryption key and an encryption of that, which is called an encapsulation of it. And the reason you do that in one go is that it allows you to accommodate these other kind of algorithms where they're not doing encryption as such. So for elliptic curves, for example, what it's doing behind the scenes is doing a kind of key agreement step that is then deriving a key. But then the rest of it works the same. So you get this random data encryption key that comes down, and then your dem, which is really an AEAD in practice, you use that to encrypt the rest of your message, and then you send the encapsulated data encryption key and your ciphertext over to Bob, and he can call a decapsulate method with his private key, which will be able to recover the same data encryption key, and then he can decrypt the rest of the message. So on this slide, there's a kind of logical communication here that there's this encapsulated key that goes between the chems and then the ciphertext that goes between the dems. In practice, that encapsulated key, you just prepend it into your message. So they're actually going as one single message. So that's the approach. And that's what Tink implements. And it implements this all in one go for you in this hybrid encrypt thing, which works a lot like the AEAD. So you call your key set, you say, right, give me a hybrid encrypt, and this key set is going to have your public keys, Bob's public keys in it, and it's going to pick the primary one, it's going to instantiate this chem and dem, and then you just encrypt it and you pass in some plain text, and you can also pass in some associated data with that. So one difference here from the authenticated encryption is that this public key encryption is not authenticated. It doesn't provide any data origin authentication. So it provides integrity protection, so you can't tamper with these messages. But an obvious fact with public key encryption is you only need the public key to encrypt a message. So anyone at all, public keys are public, they're widely distributed, so anyone at all can create a message to you, and you have no guarantee of where it's come from. So there's no authentication there, there's just data integrity and confidentiality. And then the equivalent for decrypting, so we call hybrid decrypt on our key set that has our private keys in it, and then we can decrypt a message again with some associated data. So there's a couple of algorithms they support. They support something called ECIS for this, which is elliptic curve integrated encryption scheme, which is kind of a well-known thing that lots of people do. It's a way of encrypting with elliptic curves. But it's not any particular standard. This is just Tink's own kind of interpretation of that idea, as far as I'm aware, and so it's kind of, it'll interoperate with other Tink libraries, but not anything else. And they also implement this standard from a year or two ago called HPKE, which is hybrid public key encryption. And HPKE then kind of standardizes this approach, and it has a standard version of ECIS, and it has standard things. And that has become the kind of standard that post-quantum cryptography will be done through. So all of the post-quantum algorithms are going to be integrated into HPKE, and the idea is that then if you're using HPKE, you can easily move to these post-quantum things. And because you're using Tink and you're using these key sets and you've got this cryptographic agility, you're all set then when these come out to move to them with no impact on your, or minimal impact on your systems. So there are some limitations to this in Tink at the moment. So their public key encryption is single recipient at the moment. So you can encrypt a message to Bob, but if you want to send the same message to Bob and Charlie, you have to encrypt it twice at the moment. Whereas with old style RSA encryption, you could just generate that one AES key, use it to encrypt your message, and then encrypt that AES key to both Bob and Charlie. And then it's an efficient way of kind of doing it. There are ways to make this work with chems and dems, but to be most efficient, you want that to happen within the chem itself, and that's not supported at the moment. And likewise, I said there's no authentication. So HPKE does support authentication. So there are things called authenticated chems, which do provide data origin authentication. So you provide your private key and Bob's public key, and the way that it works is it kind of combines those in a way that Bob then, when he decrypts, knows that it could only possibly have come from you. Unfortunately, that pretty much only works for elliptic curve and Diffie-Hellman based encryption, and we don't know how to do that with any of the upcoming post-quantum algorithms. So that's, I think, why Tink doesn't support that, because it's kind of looking to the future. It's possibly something that we can't actually support. So if you want to do authentication, you have to sign and then encrypt. So you sign your data with some private key and then you encrypt it. So that is the talk. So the summary then, so Tink provides a kind of high-level approach for writing cryptographic code, and it makes it easy to miss all of these really easy to mess up things that old-style crypto libraries can run into. And it's built around two key design principles. One is the cryptographic agility, that you should be able to easily move to new algorithms because things change over time. And the other is that crypto code is sensitive code and it needs to be easy to review. And we looked at some of the features around that, such as having these specific types for specific primitives with guaranteed security properties, and some of these things where they highlight potentially insecure stuff. Okay, that's the talk. So was there any questions? Yes?
So the keyset example that you showed, that like 3 keys and 1 primary key.
Yep.
And the other keys, they were associated with different algorithms. Is it used for rotating, or is it are they used for another purpose?
So they're all, if I try and find that, right back at the start, I think. So the question was, with the key sets, you have a primary key and then some secondary keys, and they each have their own algorithm. So all of the keys in a key set, where is it? There we go, are supposed to be for the same purpose. So let's say you're encrypting your database or something like that, and you're starting, say you've started over here with this AES GCM key, you're thinking that's a good algorithm to use. And then rotating it, and at some point you say, or maybe somebody's found a security vulnerability with AES GCM, or less likely, you just, for regulation reasons or something, you want to move to a different algorithm. So now you've made this your primary key and you're decrypting your new database, but maybe you've stored some backups of your database, right? And you want to restore from backup, but it's encrypted with AES GCM with this old key. And so that's why they have the individual algorithm associated with the key, is that when you restore that backup, you've got to use, if you try and decrypt with that key using char 20 poly 1305, it's not going to work. Any other questions?
Yeah, maybe I also have a question.
Mm-hmm.
So in the talk you said a lot that Tink really makes it easy to use it in the right way,
Mm-hmm.
and makes it difficult to use in the wrong way. And that's where you have, I guess, trust in Google, right? Because Google has made the thing. But I've just done an internship where they said, don't trust the big corporations because a lot of the times they're actually not secure, right? So I don't know what you think.
Yeah, I mean, it's an interesting question. I mean, like I said, there's different teams in Google and different things. Knowing as I do the people who kind of originally designed Tink, I do trust them, and they are experts, and so they do know what they're doing. But yes, it is a question of do you trust them? But
it's a rather philosophical question, right?
Yeah, I mean it's the same with everyone. Do you trust the developers of OpenSSL or Oracle who are writing the Java crypto libraries and things like that? Who do you trust unless you roll your own, and you should never roll your own crypto. Yeah. Any more questions? Great. Thank you very much.